Okay, how are we doing so far? I would like to look at number 12 from the handout. And then I would like to talk about the squeeze theorem. Okay, so we're asked to find the limit of f of x as x approaches 2 from either side. That's our question. And we're given f of x equals 4 minus x squared for x less than or equal to 2, and x minus 1 for x greater than 2. What type of function is this? Awesome. Very good. This is a piecewise defined function. Excellent. Great. So as we discussed, or we started today with the limit of f of x when x approaches 2 from either side. What does this mean? That the right-hand limit equals, yes, whatever that is. So as you see, what happens here, to the left-hand side of 2, we have this function. To the right-hand side of 2, we have this function. So in order to find the limit from either side, what do I have to calculate? The limit from the, and the limit from the, and if it happens that they are the same, what will I say? Let's say it equals 10. What will I say the limit from either side is? What if this one is 5 and this one is 10? Very good. So let's find the limit as x approaches 2 from the left, and you'll tell me of which expression, and the limit as x approaches 2 from the right, and you will tell me from which expression. So from 2 from the left. Very good. This is a polynomial. No headache whatsoever. The answer. Very good, Chris. Thank you. And 2 from the right. So what do I conclude about the limit of f of x as x approaches 2 from either side? Excellent. Very good. Well done. Okay, so the last thing that we need to address here is the squeeze theorem. Before we look at applications, let's see what it means and what it says. Let's first talk about common sense, and then we'll write a theorem. Ready? Okay. Let's suppose I have a function that looks like this, like a parabola, right here. And let's say I have another function that looks like a parabola, sort of, doesn't have to be a parabola, like here. And let's suppose that I have a function squeezed between these two, near a number. Not all the way. I don't care about all the way. Just, let's say, near 5. Here's 5. And near 5, I can show you that the middle function is squeezed or sandwiched just right there in a small open interval around 5. It's squeezed like this. But I have to show you that. That's step 1. Step 2, I calculate the limit of this and give me a number. As x approaches 5 from either side, or one side, doesn't matter. So let's say the limit is 10. Let's also say that the limit of this, when x approaches 5, is also 10. What can you say about the limit of the sandwiched function as x approaches 5 from either side, or one side, or both?
It's the same.
Right? That's the squeeze theorem. So let's take a look. Let's look at a picture in which I have, here's one function. I'm going to call this g of x. Let's say this is another function. I'm going to call this f of x. And let's say another function h that does this. And this is our a. and this is the tiny open interval. Two hypotheses are required here, or the theorem has two hypotheses. Here's the first one, that h of x is squeezed between f of x and g of x. According to the graph, it is. And number two, that the limit of f of x as x approaches a and the limit of g of x as x approaches a both exist and are what? Exactly. Let's say equal to L. From 1 and 2 by the Squeeze theorem, we conclude that the limit of h of x as xx approaches a from either side must be 2 must be equal to L. Thank you. One more time. If I show that the function is squeezed between f and g, and I determine the limits of f and g, they both exist and are equal to the same number L, then from the first and the second hypothesis and by the Squeeze theorem, we will be able to say that limit of h of x must be L. Question: why on earth will I need this theorem? In cases in which there is nothing else that works. Just this. Ready for examples? Here's the first one. Back to the handout. Example 11. Limit as x approaches 0 from either side from x to the fourth cosine 2 over x. Do not write this. I want to do this. Limit as x approaches 0 from x to the fourth multiplied by limit as x approaches 0 from cosine 2 over x. It's a limit law. I want to use it. Why did I say don't even bother? Because this exists, but this does not. What is 2 over 0? It's dne. What is cosine of dne? So, therefore, this is not the right or the correct way. Good. So, my only thought is the Squeeze theorem. Why? Because there is nothing else I can do. I will start with cosine. Why I start with cosine? Because I know that cosine is a type of function that we call it's bounded. It cannot go to infinity, cannot go to negative infinity. It's bounded. By what? What is the maximum possible value for cosine? Of anything, yes. And what is the minimum possible value for cosine? Correct. It's a bounded function. So whatever cosine, it's between -1 and 1. Let me come back to the Squeeze theorem for a moment and tell you what I'm trying to do. I'm trying to fulfill the first hypothesis. I'm trying to find a way to show you that the function we want to find the limit from is squeezed between two functions. So I'm trying to build that. I'm not there yet because I don't have my h of x inside yet. Okay. So now I'm not cheating, but I have to look at what this is. So I have this piece inside, but I really want to have this piece inside. What should I do to all three sides to get this function in the middle? By? Right. However, pay attention to two things, two concepts. One, concept number one, you cannot multiply by 0. We cannot multiply by 0. So I have to make sure that x to the fourth is never 0. But I know it's never 0. How do I know it's never 0? Because this specifically says x approaches 0 is never 0. So the first condition is fulfilled. I can multiply all three sides by x to the fourth because x to the fourth is not 0. Okay. Second very important concept. Know the sign. You must know the sign of the expression you multiply by. Must be certain or know the sign of, in this case, x to the fourth, the expression we multiply by. I must know the sign of the expression we multiply by. How come? So what? Why? Because I'm multiplying an inequality. If I multiply by a positive number, the inequality symbols will not be reversed. But if this is a negative quantity, what do I have to do here? Right. So now, can anyone tell us what is the sign forever of x to the fourth? It's always positive. So I'm safe for two reasons. It's never 0 and it's always positive. So I don't have to worry about switching the symbols of the inequality. So then, can anyone multiply and tell us what we have on the left? What do we have in the middle? What do we have on the right? Obviously, we created in this process a function that is f of x and another function that is g of x. And in this process, on number 1, we showed that our function x to the fourth cosine 2x is squeezed between two functions. The top one, x to the fourth. The bottom one, negative x to the fourth. So we fulfilled the first hypothesis, the first condition of this theorem. Now I have to verify the second condition. So this was number 1. What is the second condition that must be fulfilled? That the limit as x approaches 0 from negative x to the fourth, awesome, and the limit as x approaches 0 of x to the fourth, yes, they both exist and they are equal. Or do they exist? Are they equal to what? Since they are polynomial, I don't have to worry about anything, and the answer is good. Since they both exist and they are equal to 0, because I plug in 0 in x to the fourth, then I will say by the squeeze theorem and from 1 and 2, we conclude that the limit as x approaches 0 from x to the fourth cosine 2 over x must be 0. This could have not been done without the squeeze theorem. Any questions? I'd like to look at one more application with the squeeze theorem. Let's see, I have 10 more minutes. So I would like to look at another application with the squeeze theorem and then show you an example with the absolute value. Like, for example, this problem in number 2. Okay, so first another example with a squeeze theorem. 38 on page 107. 38 on page 107. We are told that 2x is less than or equal to g of x which is less than or equal to x to the fourth minus x, to the fourth. X to the fourth minus x squared plus 2. For all x, this happens all the time. In other words, for all x values, they're asking us to find limit of g of x. Find limit of g of x as x approaches 1 from either side. We are given a condition that g of x is squeezed between 2x and x to the fourth minus x squared plus 2 for any x. We are not given the function g of x. In this case, without the given information, I will never be able to find the limit without what I have in the first row, right? How will I find the limit if I don't even have the function? But this is a specific situation for what? Right. Because I already know that this is f and this is g and this is my h of x in the middle, right? So the first hypothesis of the theorem is already fulfilled because this is given to us. This is the first function, the bottom function, and this is the top function. Top. So the first hypothesis is fulfilled. Now I need to show what? So the limit of 2x when x approaches 1. Exactly. And the limit of x to the fourth minus x squared plus 2 when x approaches 1. I must show that they both what? Exist and they are the same. Otherwise, I can't determine this ever. So what is the limit from 2x? 2. It's a polynomial. I plug it in. I'm allowed to. I have a theorem that allows me to. And same thing, polynomial. 2. So then what do I conclude? Therefore, by the Squeeze theorem, n1 and 2, limit as x approaches 1 from g of x must be 2. So this is another application of the Squeeze theorem in which we were not even given the function. Good. So we'll conclude today. Allow me to pick some problems for you for Monday. And then we'll look at the absolute value. So on page 107, 17, 23, 27, 31, and 39. No, we did 39 together. And 37. I will try to keep it to 3 to 5, not more. Please redo the problems we did in class first. Okay, so I still have 5 minutes, yes. Okay, so limit as x approaches 0 from the left, from 1 over x minus 1 over the absolute value of x. This is not a trivial limit. This is not an easy situation at all. It has several steps. And we will find other examples and work on them next time. But let's start with this one. Can anyone refresh our memory on what does the absolute value of x mean? Right? So it's either, correct. So it's either x when x is greater than or equal to 0, or negative x when x is less than 0. This is the formal definition of the absolute value. Formal definition of the absolute value. formal definition of the absolute value. This is something super important for your notebook. Okay, so I know now what this represents, but I want 1 over x in absolute value. Can anyone give us this piece now? This one has 2 options because this one has 2 options. The bottom has 2 options, and then this fraction has 2 options. What are the options for this? 1 over x when
1 over x
when x,
greater than.
yes, but at this time I cannot put it equal to 0. Why I cannot no longer put equal to 0?
Because you can't have 0.
It's in the denominator. And what is the other option? When the denominator is negative x, then negative 1 over x for x less than 0. Okay, now I have this piece. And now I want to put the whole thing together. So I have 1 over x minus 1 over the absolute value of x. One over x minus the first option. What do I get for x greater than 0? 1 over x minus the first option. Excellent. What is the second option? 1 over x minus negative 1 over x. 1 over x plus 1 over x, which is 2 over x. Only now I'm ready to determine the limit. I look here and I identify which side. 0 from the left. Which one is 0 from the left? Top or bottom? Very good. Bottom, 0 from the left. This is 0 from the right, this is 0 from the left. So this is limit Sx approaches 0 from the left from 2 over x. Plug it in, what do we get? 2 over 0, I don't like it. So I have to go with 0 from the left, negative 0.1. So the answer would be negative infinity. Awesome. Very good. Very good.